So if I give you an equation of a line like this, y equals 0.5x plus 2. The slope of the line is positive 0.5. The y-intercept is 2. Now I can use that line to make predictions. If that's the equation of the line, what would y be when x is 0? Well, let's plug in 0 for x. 0.5 times 0 is 0 plus 2. 0 plus 2 is 2. So when x is 0, y is 2. And that, in fact, is the y-intercept here, 2. Does that make sense? And if I gave you some other value of x, like 10, then you would say, well, according to this line, y would be 0.5 times 10, which is 5, plus 2 is 7. If x is 10, y should be 7. So for any value of x, you can compute what the predicted value of y is on that line. So how do we find m and b, or beta 1 and beta 0, if I give you a data set of x values and y values that form a cloud of data in 2D? How do you find the values of the slope and the intercept that minimize the sum of squared residuals? You can do trial and error. Just try one, pick one at random and try it. And then, that seems big. Let's try a different one. And fiddle around until it minimizes. That would be an iterative optimization technique. But we don't have to do that. See, I told you there'd be ugly formula. You don't have to memorize that or use it. Why am I showing you? I'm just showing you because it just so happens that given a cloud of data, given a set of x and y values, there's an analytic expression that will give you the intercept and the slope that minimizes the sum of squared residuals. So all you need to do is churn through those calculations and you'll get the intercept and the slope of the line that minimizes the sum of squared residuals. It will give you the line at best fit. So that's nice. And the formula, it looks ugly, but it's just a bunch of sums. You sum all the y values, you multiply that by the sum of all these x values squared, and then you subtract some other sums and divide by some other weird stuff. In old school textbooks, you'll see examples like this, where you have some x data, some y data. You take x squared, you take y squared, you take x times y, and you sum them all. And then you have the components of this formula, and you just plug them in. On exams, I had to do all this by hand in my undergrad staff classes. It was a real nuisance. So we don't have to do that anymore. Sample calculations based on that if you want to go through them, but we don't have to do that anymore. We can use R. So here's some example data. 1, 2, 3, 4, 5, 6, 7 data points, x and y. Here's the line of best fit. That's this data set. The slope is minus 0.221. The slope is negative because the line, oh, I'm sorry. Wait, that's not the slope, I lied. That's the y-intercept. The y-intercept is negative 2. The slope is 1.19. So the slope is positive. The slope is positive because as x increases, y also increases. The y-intercept is negative. Why is it negative? That means when x is 0, so over here somewhere, the line would cross the y-axis at minus 0.221. And you can see that in the formula. If you plot in x is 0, 0 times this is 0, and it's just minus 0.221. So how to do this in R? Let's say you have some x data. I just copied those data from over there, and some y data. There's 7 data points. You can actually just write some simple R code to do those calculations and find the y-intercept and the slope if you want. You don't have to ever again, because fortunately there's a command called LM, linear model, that will do it for you. You give it this little formula that says y squiggly wiggly x. Anyone know what that actually is called? Yeah? Tilde. Tilde. Yeah. Tilde. Tilde. Yeah. The way to read it in R is y varies with x. So y is the dependent variable, and x is the independent variable. So the first thing here is the thing you're trying to predict, and you're predicting based on varies with x. And where are y and x? They're in a data frame called df that I've defined here. That's what this says. Okay, so I have x, I have y, I put them into a tibble or a data frame, then it looks like this, it's like a table. Then I can feed that table to LM, and I can say, what kind of model do I want? I want a linear model where y varies with x. Y depends on x. I'm predicting y based on x. And the output of that command is it's called a model object in R. That's just fancy talk for, it's a whole bunch of stuff that you get as a result of that linear model command. You get the coefficients of the line, the intercept and the slope, and you also get a whole bunch of other stuff. You get an R squared value, and you get residuals, and you get all sorts of stuff that you can unpack from that model object. If you type coef for coefficients of the model, it will show you the model coefficients, the slope and the intercept of the line. Okay, so we don't have to do any of those calculations by hand. What LM does under the hood is essentially that for an x and y variable. We'll see later in the course, you can create a linear model that doesn't just involve one independent variable, but multiple independent variables. That's multiple regression. And in fact, when one or more of those independent variables is not a continuous variable like this, but a discrete variable or categorical variable, then when you do this command, you're performing an analysis of variance. So we'll see later in the course, ANOVA, analysis of variance, is the same thing as linear regression, just with a categorical variable. They're all linear models, but that's still linear. Okay, so ln will do the line of best fit, and you can extract the coefficients using coef. If you want to plot the line of best fit, you can use ggplot. Here I just use geom_point to plot the points, and then the geom_smooth command, if you tell it method equals lm, it will draw a smooth version of the data that is the line of best fit. ln stands for linear model. And then if you want to display the equation up here, there's a special command called stat_poly_eq. It's a little esoteric, but just in the case where you want to display the model, you can use that command. Okay, so try that on your own in RStudio later. So reminder then, so the y variable is always the variable we want to predict, and we want to predict it based on an x variable. And the line of best fit is the one that minimizes the sum of squared residuals along the vertical axis. And the line of best fit is defined by slope, beta 1, and an intercept, beta 0. Any questions about that? Yeah.
Earlier you said that we need the linear model, the predictions, to compute the residuals.
Yeah.
But we also need the residuals to compute the line. So
Yeah.
is this equation doing all of that simultaneously?
Yeah, so the question was, I said that we need the linear model to generate the predictions. And we need the predictions to compute the residuals. So it kind of sounds circular, like how do you start? The analytic expression I showed you is the result of some calculus that, I don't know, 100 years ago or something, that is sort of a mathematical proof that this is the line that will minimize the sum of squared residuals. So it kind of does both at once. Yeah. The other method I mentioned is iterative optimization method, and that kind of method that people use with more complicated models than this. You basically start with a random guess about your model, and you compute the residuals, and then you try to fiddle the model up or down, left or right, and see what the residuals are now. And if they're bigger, then you go in the opposite direction, and if they're smaller, you keep going in whatever direction that is. So you kind of twiddle the line until you gradually reduce the sum squared residuals. The downside of that is it takes more computation because you have to sort of iteratively reduce the error over time. But that's a method that's used for more complex models and nonlinear models. But for linear models, the bottom line is that you can prove mathematically, and that's where that formula comes from, that there's one line that minimizes the residual, and that's the one. So you kind of do it at the same time. Yeah.
Sorry, what does the I stand for? The Y-I-X-I?
Oh, good. Yeah. What does the I stand for? So, and here. We'll see that notation come up again. I basically stands for which of these. So here there's 10 different observations in X and in Y. I just means which one you're talking about. So this equation means the ith value of Y. So for example, the third value of Y equals beta 0 plus beta 1 times the third value of X. So I indexes into the data set.
Okay.
Yeah. So the estimated value of the ith value of Y. So if I is 7, we're saying that's the value of Y that we observed in the data. But the model's prediction about the 7th value of Y is beta 0 times beta 0 plus beta 1 times the 7th value of X.
So shouldn't the Y-I, let's say that the arrows point to, shouldn't that have a number, Y number?
Yeah, exactly. It's true. Yeah. This I should actually be 1, 2, 3, 4, 5, 6, 7, 8, 9. Or 10. Yeah, 10. It's true.
Okay.
Yeah.
Okay.
I could have easily written Y10, Y hat 10.
Okay,
That's probably what I should have written. Yeah. Okay, should we go on? So we saw how to compute the model in R. We saw how to get the intercept and the slope. What does the y-intercept mean? It's the value of the line. It's the value where the line crosses the y-axis when x is 0. So in this made-up example, where x is height of people and y is weight of people, inches and pounds, the line that best fit through this data is the slope is 2.6 and the y-intercept is minus 7.2. So the slope tells you the rate of change of y given a unit change in x. So 2.6 means that if I change height by 1 inch, then weight will increase by 2.6 pounds. Okay, so the slope has meaningful units. The slope is always in units of the y variable. And it means if I change the x variable by 1 unit, whatever the units are, then the y variable will change by that many units in y. So according to this model, for every extra inch someone is tall, they will weigh 2.6 more pounds. Make sense? For the y-intercept, minus 7.2, what that means is if someone is 0 inches tall, they will weigh minus 7.2 pounds. So both of those concepts are sort of questionable. If someone is 0 inches tall, they probably weigh nothing. So why would the model say they weigh minus 7.2 pounds? Why would that happen? Is this whole enterprise just flawed or what? Yeah?
It's because it's going beyond the data that it's given. Because the line is just continuing from a best fit. But the data that we have, it will be 0 weight and 0 height. Naturally, right? The line, it's not taking that into consideration. It's instead doing it logically.
Yeah, so the answer was that by even asking the question, what would weight be when height is 0, we're going way outside the range of the data that was used to fit the line. The data that was used to fit this line ranged from 55 inches up to 82 inches, 83. So between sort of 55 and 83 inches. That was the range of data we used to fit that line. If we jump way outside that range and say, well, what about 0? We'll get an answer from the line of best fit, because this line just keeps on going out to height equals 0. And it'll give us an answer, but it wasn't fit using data that occupied that range. So it's not generally a good idea to extrapolate a prediction way outside the range of the data that was used to make that model. Yeah, and the fact of the matter is that you probably had data where you sampled people's height and weight all the way down to, height 0. It wouldn't be linear. It would probably taper off into a sort of a curvilinear exponential kind of a situation near 0. So a straight line wouldn't be appropriate. Right, okay, so this is our notation then. The ith predicted value of y, the I indexes into which data point you're predicting. The little hat is notation for predicted value. So y hat I, the predicted value of y for the ith data point is beta 0 plus beta 1 times the ith value of x. And I varies between 1 and the number of data points in your data set. I've added a little tiny Greek letter here, epsilon sub I. And you might see that in some of the readings. That refers to the residual. That refers to the error or the residual. So what this means is that the observed value of y, because there's no hat, right? The observed value of y is equal to the estimated value of y plus the residual. And that's just a statement of the geometry. You've got the actual value, you've got the predicted value, and the difference is the error. So the observed value is equal to the predicted value plus the residual. And what is the predicted value? The predicted value is that linear equation. All right. Any questions? We'll do one or two more concepts and then we'll take a break. Okay, how do we quantify how well a line fits the data? We know that we can find a line that is the line of best fit. That means of all the different, infinite number of lines we could fit, we can find the one that fits best. But how good is best? How good is that fit? It's never going to fit perfectly unless the data points literally fall along a perfect line. And they never will. So how good is the fit? How well does that line model the way that x and y covary? So one common measure of regression fit is actually r squared. And you saw r squared already last term in the lectures on correlation, right? R squared is a measure of what? Well, r squared is r, literally r squared. So what is r in correlation? It's Pearson's r, right? So, and what is r, what values can r take on? In the back.
Negative 1 to positive 1.
That's right, from negative 1 to positive 1. So an r value of negative 1 means there's a perfect negative correlation between x and y. Plus 1 is a perfect positive correlation, and 0 means no correlation. And so when you square r, you get r squared, and that can vary between 0 and 1, because negative value squared becomes positive. And r squared, essentially, it represents how much variance in the y variable can be explained by the x variable. And in the context of linear models, it's a metric of how well your model fits the data. If r squared is 1, then it's a perfect fit. If r squared is really close to 0, that means it's a terrible fit. You can still have the line of best fit, it's terrible, right? That's the best it can be, and the best is terrible. Here's the formula for computing r squared. It's 1 minus the sum of squares residuals over the sum of squares total. The sum of squares residuals is the sum over all observations of the observed value minus the estimated value squared. So just like we talked about, the difference between the observed value and the predicted value is the residual. We square them and we sum them. That's called the sum of squared residuals. That's the quantity that's minimized when we put the line of best fit. We can also compute sum of squares total, which is the sum over all observations of each observed value minus the mean, the average value. Square those, and that's called sum of squares total. We take the ratio of those two and do 1 minus that ratio, we get r squared, which varies between 0 and 1. So you can kind of see, if sum of squares residuals is the same as sum of squares total, then you've got some number divided by the same number, which is 1, right? And 1 minus 1 is 0. And so r squared would be 0. So you have a terrible fit. So if the sum of squares residuals, if the vertical distances between the predicted values and the observed values were no better than the differences between the observed values and the average value, then you haven't really done much. You haven't improved the situation. What would that correspond to? Imagine a cloud of data. Find a cloud of data. Let's look at that cloud. If the sum of squared residuals, the sum of squared of these vertical red lines, was exactly the same numerically as the sum of squared differences between each black dot and the average y value. The average y value is just a horizontal line, right? The sum of squared residuals of the line of best fit was the same as the vertical distances between each data point and a horizontal line. Then what would the line of best fit be? It would be the horizontal line. Yeah, your line of best fit would just be rolling. It would be a horizontal line going through the average value of y. So the y-intercept would be the mean of y, and the slope would be 0. That's a pretty dumb model. It in fact is no model, right? The model you come up with is just take the average value of y. What you're saying is, okay, I want to predict y from x. Well, no matter what x is, y is just going to be the average value. Right? It's not a very useful model. You're basically saying, I don't know how y varies with x, so just use the average value of y for all your predictions. So if these two are the same, then you're essentially just using the average value of y, and your model is no model at all, and r squared would be 0. If this quantity is really close to 0, and 1 minus that quantity is close to 1, then if this is close to 0, that means that the top is much smaller than the bottom. Right? The sum of squared residuals, the vertical distance between the data points of the line of best fit, are way smaller than the vertical distance between the data points and the average value. If you imagine a horizontal line and the vertical distances, and your line of best fit, and now you have teeny tiny vertical distances, that means you fit the data really well compared to not fitting it at all. Right? A small number divided by a big number is a small number, and 1 minus the small number is going to be close to 1. So when r squared is close to 1, it means you have a really good fit. The model fits really well. Does that seem reasonable? So here's two examples of data sets. Here we have a line where the data don't depart much vertically from that line, and the sum of squares residuals is 1.9. The sum of squares total is 82.6. And r squared in this case will be 0.98. It will be really close to 1. So that would indicate a really good fit. Here's a different version of this where there's much more variability along the y-axis. Now the sum of squared residuals, which is the model-based fit. The error metric is 46.5. The sum of squares total is 120. So they're not as different as these ones were different. And now r squared is 0.61. Much less. It's much farther from 1 than that one. So 0.61 would be this model fits this data worse than this model fits that data. And if you get an r squared really close to 0, it probably means you have a line that's almost horizontal. Yeah.
So I know we're focusing a lot on the linear regressions, right?
Yeah.
But out of curiosity, if we had a whole bunch of data, right?
Yeah.
And then we somehow found like, I don't know, like the quadratic or some other equation that can fit and is like best fit there.
Yeah.
Is r squared still applicable in that sense? Because we do have a y predictor and we also do have a mean, right?
Yeah. Yeah, so the question was, we're talking about linear models here, but in principle, if we came up with some other equation, some quadratic or even a polynomial with multiple terms that had some, squiggly wigglies that went through the data even better, could we still use r squared to characterize that model's fit? And the answer is yes, we can. Yeah, there are other metrics as well, but we can certainly still compute r squared because we still have a sum of squared residuals and we still have a sum of squared totals. Yeah. Yeah. R squared as a measure of linear correlation depends on the model being linear, but r squared as a measure of general model fit to data, it doesn't have that dependency. Yeah, we're not going to really cover nonlinear modeling in this course, but it does exist and it's out there. And it's becoming more popular now because packages like R can do it much more easily and more friendly than in the old days. Okay, I mentioned something about variance. R squared has another conceptual meaning. The value actually corresponds to the proportion of variance in y that can be accounted for or explained by variance in x. So if r squared is 0.78, it's pretty close to 1. That means that 78% of the variance in y can be explained by the x variable. Variance just means how much y changes from observation to observation. So those changes can be, 78% of those changes can be accounted for by changes in x. If r is 0.22, then r squared is 0.048, which would mean only 4.8% of the variance in y can be accounted for in x, so that's much less. 78% is much bigger than 4.8%. So as r, not r squared, as plain r gets smaller and smaller, r squared gets even smaller and smaller and smaller. So that's an important concept. R squared is the portion of variance in y that can be explained by x. All right, let's take a break. Let's take a 10-minute break, and we'll come back and talk about another measure of fit.